Okay, so today I will finish the first semester lecture by defining what are the Virelizier invariant. It's another quantum invariant of three manifold defined by state sum method. Okay, so these invariants are defined using some algebraic data, so I will explain it. So the algebraic data used to define the Virelizier invariant consists in the following. First, we have a finite set I, and whose element will color the edges of a triangulation. Then for each element of this set, we consider an invertible element, let's call it di. And here K is a commutative ring. We need also another element, invertible, that I will denote by D in this ring. So as I said, the element of the set I will be used to color the edges of a triangulation. But it cannot be colored in any way, so we want a notion so that for each triangle the colors are compatible, like in the Disgraf-Witten invariant. So here we need a distinguished set of unordered triples of elements of I, and we call these triples are called admissible triples. And then we want to associate scalar to the tetrahedra, so we need for any ordered 6 tuple I, G, K, L, M, N of element of I, we want that this sixth tuple is admissible, so which is admissible in the following, in the sense. So we want that the triples, so I, G, K, K, L, M, G, L, N, and A, M, N are admissible. So I will explain later why this definition.
So A is I?
Sorry.
Okay.
So for each six tuple which is admissible in this sense, we need an element. I will denote it by this. I, G, K, L, M, N in the ring that we called the symbol in the literature, 6G symbol of the sixth tuple. Okay. So we need this data. But of course, this data should satisfy so the following actions. So we want first I will give the action and then I will explain them during the construction of the invariant. So the first action, I call it symmetry, means what? So now for any admissible six tuple, so I, G, K, L, M, N, we want the following equality of the symbol, so I, G, K, L, M, N should be equal to I, K, G, L, N, M should be equal to G, I, K, M, L, N. So then equal to NMK I G N I M N LGK, and finally LGN IMK. Okay, so we want this equality. maybe I make a remark. Note that these symbols are well defined because here there is other 6 tuple because the involved 6 tuples are admissible. For example, let's say, look at this one. LMK IGN is admissible because we want LMK, so LMK is here by this condition. And you can check this. So this is well defined. This condition is well defined. So this is the first condition. We want some symmetry. Now there is a second condition called orthogonality. Okay, so I will just take my, just write it. So for all, so A, B, K, and N in the set I such that the triple, so A, B, G, A, V, K, G, L, N, and K, and N. So we want that this unordered triple are admissible. So we want the following condition. So the sum where C of dC dj of ADG LNC times ANC LBK is delta GK. So I will call this relation, let's say, A. And there will be a second relation later I will use, so I left some place here. So the relation A holds, where here, in this relation, where the sum is over all the elements C in I, such that the symbols are defined, and when you look at the definition, we want that this triple, these 6 tuples are admissible. This means that the triple CAN and CBL are admissible. So this is the second condition on the data. The third condition is we know that for those who know representation theory, it's called the norm Elliott identity. Okay. And so what does he say? So for all, so there is I, J, K, L, M, N, A, B, C in I, such that the sixth tuple, so I, J, K, L, M, N, and A, N, A, N, C, L, B, J. So we want that these six tuples are admissible. So the relation B, I will write it holds. So let us call, so the relation B is the sum for D of I, J, K, B, D, A, K, L, M, C, D, B, and I, M, N, C, A, D is equal to I, G, K, L, M, N, L, N, G, A, B, C. This is the condition B. And here, where the sum is over all D, again, such that these symbols are well defined. So the first condition implies that these two are defined, and for the other symbols to be defined, we need the following. This. So the condition is that DI, DBK, and the DNC are admissible. Okay? And finally, we want another, so condition for all, so G in I, we want that, let's call it C, the number, the sum about over A, B, such that of dA, dB, and I take di inverse is equal to d, the sum, where the sum is over all AB in I such that IAB is admissible. Okay. So this is the initial data. Then we will see an example later. But okay. So now, as I said at the beginning, oh sorry. So the samples are defined. That is, and the conditions are admissible.
Should this condition 4 have a name?
Yeah, you can say normalization if you want. So, okay. Now, as I said at the beginning, the color, the element of I will color the edges. So first, let us talk about the colored tetrahedra. So, I will say that the tetrahedron is colored if its edges, let's call it delta, if says are endowed with elements of I such that for all triangle T of delta, the colors of the edges of T form an admissible triple. Okay. So I will keep this formula. So I make a picture. So we have a tetrahedron. And we have colors. Let's call it I, G, K, L, M, N. So the edges are endowed with color in the set I. And for each triangle, the triple of color is admissible. So here, I, J, K, K and M, G and N, and I and N are admissible. So in other words, this means that, so for the definition, then the six-tuple I, J, K, L, M, N is admissible. Admissibility for a six-tuple. Okay. Now, if we have a tetrahedron, which is colored like this, we would like to give a symbol. So, but such, so the colored tetrahedron delta, so it gives rise to so 4 times factor 3, so this should be 24. Admissible six-tuple. So how are they obtained? So for each triangle, so you pick a triangle of the tetrahedron. And how do you obtain? Could you obtain an admissible tuple? So you take the color of the triangle. So the color of the edges of T followed by the colors of the opposite edges. So opposite means in the tetrahedron edges. Okay, so let's see an example. Now, if I take, for example, this triangle, first triangle, IGK, so I can take as the color IGK, no. I revise. For example, let's say, the triangle TIGK gives the following 5, 3, 6 admissible six-tuple. So there is this. So what do? You take the color of the triangles. For example, I can take IGK. Now the opposite edge of I is L. So put L of J M. And for K is N. But now I can take another order. So the permutation of this, the edge is, the number is factor 3, so it's six permutations. So I, K, G, G, I, K, G, K, I, K, I, G, K, G, I. And so you can complete. The opposite edge of I is L, K is N, M, I, G, K. So J is N, I, L, K, M, so etc. Okay. Okay. So if you have a color tetrahedron, you have 24 admissible tuples, and what is the condition N on symmetry? So the symmetry condition, so the symmetry axiom 1 implies that all that this symbol of all of these, that all the symbol of these are admissible. Tuples are equal. So never mind which admissible tuple you extract from this colored tetrahedron, the symbol is the same. So, and we denote it like this. This is an element of K. So, for example, so if we take again I, G, K, L, M, N. So the symbol of this one is I, G, K, L, M, N. But it is also, for example, K, L, M, N, I, J, etc. There is 24 equalities. 23. Okay. So this was for color tetrahedron. So now we are ready to define the invariance as a state sum. So the state sum. Okay. So here we take M, a closed three-manifold. And we so we pick a triangulation T of N. So we need to define what is a coloring of T. So coloring of this triangulation T the map C from the set of edges of the triangulation to our set I, and we want for all triangle T of the triangulation we want that the color of the triangle form an admissible triple. The color of the edges so the color is, this is image under the R map of T form an admissible triple. Okay. For each triangle, the colors are admissible, form an admissible. Okay, now. So now if I take a coloring of our triangulation, by definition, it makes each tetrahedron of the triangulation colored tetrahedron. So this condition implies that each tetrahedron is colored. I will denote like this. And we set T with color C is defined to be the product from on all the edges of our triangulation of the number D times the product on all tetrahedra of T of the symbol associated to this color tetrahedron. Okay, and finally, we set M is the sum. So for each state, coloring can be summed as a state. For each state, so we have a number and we sum over all states. So we sum over all coloring. And so we have a normalization by D minus N0 of T, the sum of C coloring of T of these numbers. And this theorem is that this is well defined and is a topological invariant of three manifolds. And we will prove this after the break. Okay. And we will use these relations to prove this theorem. And then I will briefly explain how to obtain such example of an example of an initial data using the representation theory of UQSL2. The quantum group UQSL2. Okay. Okay. So let us prove this theorem. So now if we have a triangulation T of M, we denote this sum as this. We add in the notation T. So D minus N0 of T, the sum of C, TC. This sum is an element of the ring. Okay. So what do we have? So the following is evident. So clearly, if F is a homomorphism between three manifolds, and T is a triangulation of M, then the image of T by F is a triangulation of M prime of M prime, and if you look at the way these sums are defined, clearly we have that M, so M prime F of T is empty. In particular, the state sum is invariant under isotopy moves on the triangulation. So what we need to prove that this sum is invariant under the application to T of a partner 2, 3, or 1, 4 move. Okay, so let us check this, and of course we will use these identities. Okay, so let us begin with 1, 4. It is so we have a triangulation. And so what happened is we add a new vertex inside the tetrahedron. And new edges. Okay, like this. Now, so our triangulation T is transformed into T prime. Now, I take some coloring, I, G, K, L, M, N. If I take a coloring, so C, a coloring of T, now, how do we obtain a coloring of T prime? So C plus, so here you have I, G, K, L, M, N, and we add colors A, B, C, D, C plus 4 element A, B, C in our set such that we want that all the triangles are admissible. So ABG, so ABG, BC and CAN, no, DCK, DAG, and it remains 1, DCM, we want that these trips are admissible. This form a coloring of T prime. So you have a coloring of T plus color of the interior edges such that these triples are admissible. Okay. So now, using the state sum, the contribution of this tetrahedron to TC is just, by definition, I, G, K, L, M, N. Maybe we put it. So I put this 1 and this 2. So the contribution of 1 to the state sum so the coloring, let's call it C prime. So contribution of 1 to this number is I, G, K, element. And now, what is the contribution of 2 to T prime, C prime? So, we look at the, so the sum from A, B, C, D, the interior edges such that so the condition, yes, no, such that these strips are admissible. So we have the product of the color of the H. So here we look at the product of the interior H, dA, dB, dC, dD, and of the tetrahedron. So I, GK, so I, therefore, I, GK, B, DA, BDA. KLM KC DB. Now we have IMN and so I is CAD. And there is another one, GLN, with CAB. Okay. And we want to prove that this is equal to this. Okay. Now we look. I hope it works. So no. If I use the relation B here. Okay, B. So I can take the sum over D, DD, so HGK BDA, okay, we have here, KLM CB DB, IMN CAD. So we have this number here. So we can apply A, so we have sum of A. Oh, sorry, I forgot, because there was a, okay, so ABC, so DA, DB, DC, so this we will replace with this, so HGK element, LNG ABC, and what was not in the sum is this one, GLN CAB. No. Okay. Probability, so I'm not sure of this one. That's why I'm thinking. Here we have So I, J, K, L, M, N, A, B, C, D, G, N, N, A, orthogonality. Okay. Let us write L. So L. So L and G. A. A B C. No, GLN CAB. Sorry. GLN CAB. Okay. And now, if you look, using A with this one, so we use the orthogonality relation with these two and the symmetry, so A, B, G, L, and C, A, and C, L, B, G. Yeah, here with K is equal to G, so we take sum over A, B, dA, dB, dG inverse. We put the dG in the other sense. We use A with K, A with K is equal to G. And this is exactly by C, it is D.
There is still the EGK element symbol.
Sorry?
There is still the IJK.
Yes, of course. Sorry. IGK LMN. And this is D times IGK element. Okay. And so the difference between the contribution is just a multiple by D. Thus, MT is MT prime by, so this follows from the normalization by D minus N0 of T. Since D minus N0 of T prime is, and T prime has one vertex more, so minus N0 of T times D inverse. And this D and D inverse cancel. Okay, so we have shown the invariance under the moves 1, 4. And now the move 2, 3 is easier. Yeah? So here we have so let's say I, G, K, L, M, N, A, B, C. and how it is transformed. So you add an edge here. Like this. So let's say A, B, C, and I, G, K, L, M, N, A, B, C, and D. So here, a coloring of T is obtained from a coloring of T prime is obtained from a coloring of T by adding one color for the edge so that all the interior triangle, there are 3 triangles, are admissible. You know it right. But the contribution of one and 2. So the contribution of 1 to TC. So here see a coloring of T. And 3' coloring of T prime obtained from C by adding a color. We add the color D, such that I can write D IA D BK and DMC admissible. And the color to this sum is again the product of the symbols of the tetrahedron. So I, G, K, L, M, N times G, L, N G, C, A, B so this is this. We have symmetry. I can write it like this. Ln G. And now the contribution to T prime C prime is so the sum from D such that this triple R admissible. So we have one edge more. So D of D, and now we look. There is 4 tetrahedron, I, G, K. So I, G, K, the opposite of I. B, B, D, A. Now KLM. So KLM C D B. And so for the opposite of I is C, the opposite of M is A, is the opposite A is CAD. This works. And you know that these contributions are the same by B. So, and here the number of vertices is the same, so the normalization doesn't change, factor. So here we have proved the invariance under the 2-3 moves. And so we have proved the theorem. Okay. And you have seen that we have used to do these three conditions, plus the symmetry, of course. Now, a question is how to obtain initial data. And I will give an example of an initial data from quantum groups. So it is the thing for initial data from, we call them the quantum 6G simples. Okay. So I give the data and then I explain where it comes from. Okay, so we fix some number, integer r greater than 3, and we define a set I. This is a set of half integers, 0, 1 half, 1, 3 half, etc., until r minus 2 over 2. So this is a finite set. And we pick, let Q0 be a primitive root of order 2R. And set Q is Q0 2R. Now, if we have an integer greater than 1, we set, as last time, using the Q0 to the n, Q to the minus n, so Q0 minus Q0 inverse. And we set again the factorial n is n, so 1, 2, the quantum integer n, and for 0 we have this. We put that factorial of 0 is 1.
Sorry. What does that mean, be a primitive root of order 2r? Like, if that means this number to the power 2r is 1, then q is...
This means that qn, you take an integer, m. Qm is 1, if and only if 2r divide m.
So Q is 1.
Excuse me.
Okay, sorry.
Okay. Q has order r. Thanks. Otherwise, Q is 1. Huh?
Yeah.
Okay, thanks. And so, we already denote this. R is 0, and n is non-zero for these numbers, for r between 0 and r minus 1. And because Q0 has order 2r, you can notice that this is not only a complex number, but it is a real number. It is the quotient of 2 sign. Okay. Okay, so we have a finite set I, and we say we need the number So for I in I, the I is I 2I plus 1. Okay. So we have this number. Now I say that a triple IGK of element of I is admissible if the following condition hold: I plus j plus k is an integer, I less than j plus k, g less than I plus k, and k less than I plus g, so triangular inequalities. And this integer here, I plus g plus k, is less than r minus 2. Okay. So now, for such an admissible triple, IGK, you set this. It is I plus g minus k factorial, I plus k minus g factorial, j plus k minus I factorial, and you divide by I plus j plus k plus 1 factorial, and you take the square root. And here for x, if we know with this that this is a real number, but what I mean by square root of a real number, it is x1/2 is just square root of x if x is non-negative, and if x is negative, you take the square root of negative x times square root of, so the minus 1. So square root of minus 1 is just I. So complex number I, but I do not use this notation because I have I everywhere. And with this, you can remark that the square of x1/2 is just x. Okay. So we define these numbers, and now we have to define more. Now, for an admissible 6-tuple I, G, K, L, M, N, we set I, G, K, L, M, N is this one. Delta I, G, K, delta I, M, N, G, L, N, K, M, M, times some sum, or minus 1 z. So take z plus 1 factorial, and you divide by a big, so I write it, but z minus I minus g minus k. Z minus I minus m minus n. Z minus g minus n minus n. Z minus KLM. And so I plus G plus L plus N minus G, I plus K plus L plus N minus Z, I plus K plus L plus N. This is not good, this one. G plus K plus M plus N minus Z. So this is the denominator. And you take.
Sorry, first, the first term at the bottom. So it's written I plus J plus L plus N and minus something. It's not minus J, yes. So the first.
This one?
At the bottom. Yes, this. There is something.
I plus J plus L plus N minus Z.
Okay.
Thank you. You remove Z for this time. Okay, well, and you take Z such that denominator is non-zero. You can find the condition. And finally, I gk element is square root of minus 1 times 2I plus the sum of L plus K plus L plus M plus N I gk element. And in some sense, the theorem is that this is an initial data. So you can verify this. And maybe just, and with this data, for example, you can compute and you find for example, that for S2 cross S1, you have 1. For S3, you have minus Q0, Q0 minus square over 2R. And if you want to compute S31, for example, you have Q0 R minus 2. 3. So this is the integer part, minus Q0 R minus 2 over 2 plus 1 minus 1 square over minus 2R. Okay. So this is example. You can compute using this data, this number. But now maybe I finish with the following remark. Of course, how can you find this? So maybe, okay. So the quantum CG symbols they are obtained, so they may be obtained by studying the representation of UQ SL2. More exactly, a real form of it. Never mind. So, in particular, so you can find that there are irreducible modules. So OQ, so modules, indexed by this set of integer I, and such that we know the multiplicities of the sim. So this means such that Vi answer Vj, you can see that it is isomorphic to a sum of k, Vk, with k, I minus j, I plus j. So it's not difficult to find these modules. But then, what can we do? No. So we have that Vi answer Vj answer Vk. It is isomorphic, so here, maybe I put n, x. So here you see that you can find that sum. So which one I take? Sum 2. I take a L. L is, sorry. So we take the sum of k of Vk answer Vn, and then a sum, and it is isomorphic to a sum of Kn Vn. Which is the decomposition. And again, we can do the same game. But with two other factors. So it is the sum of n. So I will put m here. And here I put n here. So Vi answer Vn, and it is again n here, and I put m here. And again, the sum of Km, Mn, Vn. Okay. And you know that these modules are isomorphic. And so here, this is a multiplication of, if you it is a sum of KLMN of sum of the number multiplication by some number, I, J, K, L, M, N. And these numbers, when you compute with this irreducible module, gives the number I gave before. So this is a lot of computation, but it works like this. So actually, this 6G symbol comes from the representation theory of the quantum group. And it works also for other series like QSLN and so on. But of course, we have no time to do this computation. But okay. That's where come from this initial data.
So these invariants, they are the trivial invariants associated to Q0 and R, right?
Yeah.
So, I was not here 2 weeks ago, but is it like true that the representation of UQ SL2 are exactly like SL2 classified by IS?
Yeah, there is some subtlety, but it is similar. So you can find, for example,
Because this is true for like irreducible SL2.
it is similar, of course, because you know when you take Q to 1, you recover USL2. So this is.
Is there any situation where this has been used to prove something about 3 manifolds?
Yeah, so what I did not say is that, because I have no time, so this invariant extends to a three-dimensional topological quantum field theory. So you can associate to surfaces a vector space, and to three-dimensional covariance between surfaces, you associate a linear maps. And so on, and so this gives new representation in this way. But for the point of view of just distinguish 3 manifold, so we know how to distinguish them by other means. So it depends on the example of your 3 manifold, but what is important here is to understand the relationship between the algebra, the topology, and also the fact that it extends to a three-dimensional topological quantum field theory, which give other information and so on. Okay.
There should also probably be some kind of physical interpretation of this, right? Because this is.
Yeah, so this is, in some sense, this invariant is related to quantum gravity. So this invariant, the Torre-Viro invariant, is related, is a model for 2+1 quantum gravity. So gravity, so between the 2+1, 2 is a dimension, 1 is time. But of course, we would like to have a 3+1 model of quantum gravity. So I'm not expert on the physical part of it, but this is related to quantum gravity. There is maybe a book of Kashaev R, something like this. So if you want reference, you just give me an email. I send you. Okay, so thanks.